the focus of my talk to really cater a bit more to the audience here. They'll be probably more interested in some statistical seismology than some geomorphology. And before I get started, I really want to acknowledge the support of my PhD supervisors, particularly to these projects. Emily Brodsky and Thornton Wei were really instrumental and amazingly supportive in following me in different directions. Also, in the later part of this talk, I'll be presenting some work that was really made possible by collaborations with a group at the Technical University of Munich. In particular, I want to shout out Alexander Schur. We really had a cool collaboration going on this project. I've kind of stolen this slide from Nicholas van der Elst, and I really like it as it emphasizes that our observations of seismicity are just really this narrow window, but there's this entire process going on alongside. And we always see this very small window to what's going on. And my hope today is to convince you that as we build our geophysical data sets, we can find tricks and different approaches to inform earthquake forecasts by growing this window. So I'm just going to dive straight into two earthquake sequences that happened pretty early during my PhD. And I thought they were really remarkable earthquake sequences in the way that they're so darn different. So this is two magnitude 7.5 earthquakes, one in Papua New Guinea and the other one in North Honduras, one a thrust fault, one a strike slip fault. And I'll note that these earthquake sequences are remarkably different. The Honduras sequence turns off almost right away, almost no aftershocks. Magnitude 7.5 earthquake, almost no aftershocks. In contrast, this sequence is still going on as I speak, with a lot of aftershocks that kept going for months and months and months. In fact, this period of aftershock sequences is the period where the earthquake hazard is the highest. This is where the earthquake hazard jumps up by a factor of 1,000. And it's important to note that there's a typical kind of number that's thrown around for the risk of an even bigger earthquake during the aftershock sequence, which is about like 5%. But as you've seen, the variations in aftershock productivity are very extreme. And those variations in aftershock productivity map directly into this hazard of even bigger earthquakes. I think this is a very interesting period of the earthquake cycle because it's rich in data. We see earthquakes, there's deformation, it's exciting. And at the same time, it's really the period that matters. It's from a hazard perspective, this is really the very pivotal period of time where we can say where people are going to be very interested in want answers from earthquake forecasters. So early on in my PhD, I set out to do a global analysis of aftershock productivity. So using a simple Gardner-Knaupoff aftershock clustering approach. So this is really a crude approach where we just go around and look at the biggest earthquakes around the world, and we determine a sort of volume that scales with the size of the event, and we count the aftershocks. And we do this for every single large earthquake in the NEIC catalog with a catalog completeness of 4. And the result of this analysis is this pretty well-known scaling relationship between the number of aftershocks and the size of the region. And you'll see that it describes the data pretty well. If we just look at the median size of events per bin, we see that this relationship fits these events quite well, shown here by the square markers. However, I want to point out that the data is extremely dispersed. I'm talking about almost 3 orders of magnitude in the scatter around this productivity relationship. That's pretty crazy. And this is a scatter that's even bigger than if you take a very sort of low information Poisson distribution as your model of statistics of the abundance of aftershock productivity. Sorry. So this is over dispersed, extremely variable around this scaling relationship.
Sorry. Kelian, do you have a limit on the depth of the earthquakes?
I'm going to get to that. So for the remainder of this talk, I'll be investigating particularly the scatter around this productivity law, so shown here by the relative productivity. And I'm going to be using the word productive a lot, and if I say an earthquake is productive, I mean that it is has more aftershock compared to a typical earthquake of that magnitude. Another thing I'll note while I'm here is we have this constant trade-off, where if you consider smaller earthquakes, what happens is smaller main shocks, what happens is that there are a lot of main shocks that have no aftershocks bigger than 4.5. So one approach might be to be a bit more conservative in your selection of the main shock magnitude, but then you quickly run out of events. So there's a bit of a tug of war, and here we selected main shocks greater than 6.5, and we just live with the fact that there's what's so-called the so-called censoring effect, where we can't really plot zero aftershocks on a log scale. And for the remainder of the shocks, you'll see like these histograms, which are indicating the abundance, the percentage of these events that have no aftershocks. So for the first part of this talk, I'll be investigating what are the controls on the variations in aftershock productivity. And when I think of this problem, I view kind of three end members to explain this behavior. One hypothesis might be that the setting determines the aftershock productivity. So characteristics of the volume might be the control on aftershock productivity. Another end member might be that the earthquake itself, by its energetics or something like that, characteristics of the main shock might determine second order effects over the main shock magnitude itself. And finally, just might be randomness, kind of the null hypothesis we're going with. And I'll note that when we typically talk about operational earthquake forecasts, it's kind of a hybrid of these two end members here. So typically an operational earthquake forecast, when they're issuing alerts to the public, they'll essentially use by the analogy of similar nearby earthquakes to inform what might go on in the aftershock sequence. What I'm kind of interested in is whether we can inform earthquake forecasts by earthquakes that are similar in terms of their geology, in terms of what we understand of how earthquakes work. This is not something particularly controversial here, but I'm just saying that like a very deep earthquake on the other side of the world might be a better analog for an earthquake than the next nearest earthquake in the region. That's what I'm going with. Throughout this talk, I'm going to highlight earthquakes by color, by faulting style. This is an effect that's kind of documented in the literature. It's unclear whether it's like a setting effect or a source effect. That'll be the coloring for a lot of this talk. So this is the idea that I'm floating around here, is we can forecast earthquake sequences by analogy to similar events from a similar setting instead of just nearby earthquakes. So this is probably my favorite figure from this project. Here I'm plotting the relative productivity of all main shocks above 6.5. In blue are less productive, and yellow are more productive. And already, when I see this map, I see a lot of really cool patterns jump out at me. So in our neck of the woods on the San Andreas Fault, we have this contiguous area of pretty productive sequences. Immediately as we jump offshore, both to the north and the south, we have this marked drop in aftershock productivity. We have these strips in Peru and Ecuador and Chile that are really low in aftershock productivity. I think quite clearly that's the depth effect. Those are really deep earthquakes. So just from looking at this map, I feel pretty comfortable in saying that it's not all end member number 3. There are patterns here. There's something going on in terms of the aftershock productivity. It's not just random. So for the remainder of this talk, we'll be like slicing and dicing this data set to see whether there are any patterns that arise in terms of aftershock productivity. So for starters, I'll investigate setting effects. So and these are all effects that in the literature have been sort of tossed around as potentially influencing aftershock productivity, plus a few that we were interested just from looking at this map to investigate further. So depth is a very well-known effect on aftershock productivity, but we also wanted to investigate different plate boundary types, plate age, continental versus oceanic plate. So be warned that when you do aftershock statistics, you end up with a lot of scatter plots that have a lot of fluctuation, and that's just the reality of studying aftershock statistics. But moving on, if we investigate this sort of first order effect, this is a well-known effect of depth. And we can see that particularly the really deep events, I'm talking like 100 kilometers depth, or even like approaching 1,000 kilometers depth, those are events that are like markedly less productive. And there's sort of speculation in the literature as to why that is, but it really doesn't seem necessarily to be related to like a detection issue. It really seems to be a real feature of very deep earthquakes. So for a lot of the remainder of the analysis, I'm really going to be focusing on these shallower events that are deeper, shallower than 55 kilometers.
Kelian, on the left, am I supposed to see a negative slope if you were to fit data combined to that thing?
On the left. Yeah. Yes.
Okay.
I did warn you. This is like, it's not so obvious.
Well, just a different mean to the left, mean to the right. Yeah.
So these are subtle effects, but also remember that this is a log scale. So there are some rough systematics here that potentially hint at like what's going on in terms of physics. On the right, I'm plotting, and this is actually kind of new from the work that I did, a sort of relationship between the seafloor age and the aftershock conductivity. Broadly speaking, if we run a sort of median through this data, we have this increasing aftershock productivity as the plate age increases. And you can also see that in terms of the number of main shocks that just have no aftershocks, really clustered around the seafloor spreading centers. Again, I'm just going through the list. We look at the different types of plate boundaries. I would think one of the sort of things I would wish to highlight is that oceanic transform faults are markedly depreciated in aftershocks. And then as we move towards more convergent boundaries, that's where we have typically, again, on average, higher aftershock. So the next thing that we investigated was also sort of source effects. A lot of things that the literature seems to think should matter a lot, and that includes radiative energy. It also includes this really cool data set of all magnitude 7.5 earthquakes since 1990, inverted using fine fault inversions by Gavin Hayes. So this is a uniform global analysis of really large earthquakes around the world. And from these fine fault inversions, such as the one shown out here, we derive a few products, including the dimensions, the width, the length, the aspect ratio, the rupture duration, the velocity, the stress drop. We remeasured the stress drops to account for the sort of heterogeneity of these ruptures. And before I show the results, I'm fully aware that if you consider enough parameters and you try to find enough predictors, you might find something statistically significant. But we have a tool to sort of guard against this, which is to ask, given that we've observed, a large set of potential predictive predictors, what is the most extreme observation that we'd expect given this really large set of predictors? So this accounts for the effect of having looked at a lot of potentially meaningless predictors. So this plot is a bit busy, but here I'm showing sort of a linear regression against all of these source attributes as in terms of the quality, in terms of the variance reduction, considering aftershock productivity. One thing that stands out for starters is that the variance reduction, so the amount of sort of variance that we're explaining with these predictors is pretty small, like 10% of the variance in terms of relative productivity, even for the sort of best predictors. And those include stress drop and the normalized width of these ruptures, so how narrow are they compared to an earthquake of a similar magnitude. And finally, the aspect ratio seem to be sort of these parameters that affect the aftershock productivity. I think it's also interesting to note that things that I would have honestly put some money on probably mattering for aftershock statistics, didn't seem to matter. That includes the heterogeneity of the rupture. So if it was a really patchy rupture versus a very sort of uniform rupture, that did not seem to influence aftershock productivity at all, nor did something like radiated energy. So to summarize, it seems like the least productive aftershock sequences are hosted in either very, very deep environments or in very young oceanic lithospheres. In terms of source characteristic, it seems to be very long aspect ratio, high stress drop, so compact ruptures, and steeply dipping faults, so strike-slip faults that seem to have the least aftershocks. I think all of these things together are nudging kind of towards an interpretation that's pretty straightforward, saying that aftershock productivity seems to be controlled by the availability of faults. So remember that as the oceanic lithosphere spreads, it has time to cool down and becomes thicker and thicker and thicker with age. So this relationship that we saw with lithospheric age seems to really hint towards this idea that as we provide more and more space for aftershocks, we get more and more aftershocks. And then similarly, as we sort of go really deep down into a subduction zone, this is where the plates are heating up again, and again, we run out of space. And conversely, the environments that are convergent, where you're essentially sandwiching two plates on top of each other, those are the environments that seem to be the most productive, have the most available receiver faults to generate aftershocks. So this is kind of the closing slide of this little exercise here, where we said, okay, like there's all of these setting and source attributes that might contribute to earthquake forecasts, and they're a truly complementary approach to the type of operational forecast that you might do today, because they're really just using the context and information about the earthquake that we know almost right away for most large earthquakes, and using those in the sort of pretty crude machine learning model known as a support vector machine, we're able to regress those source attributes towards against a sort of predicted aftershock productivity. And the choice of a support vector machine allows for like some nonlinearity in the data. And I'll also note that we're using k-fold cross validation, which means that like every single prediction is derived from a model that is trained on everything else. So that's an attempt. It's not a perfect attempt, but it's an attempt to remove some overfitting that might arise otherwise. So here, it seems like just including these source attributes and this information about the setting, we're able to provide some sort of predictive information about what the sequence is, how the sequence is going to unfold. I think this is pretty intriguing. So I'm going to conclude the first part of my talk here by pointing out that there's really this complementary way of thinking about forecasting, not in terms of what the nearest earthquake is, but rather what is the most similar earthquake somewhere else in the world. And I think this is a really important and valuable approach to how to improve earthquake forecasts. And I think that we can also do some science here. We can start understanding what are the sort of primary effects that influence how earthquakes communicate to each other, like how does stress communicate through the crust? And it seems that really a space problem is one of the key factors in understanding how earthquakes sequence. This takes me to the second main part of my talk, where motivated by this desire to include a lot more diversity in our earthquake forecasts, I set out to try to include this information into a formal earthquake forecast. And I kind of hit a roadblock when doing this. And it was even more peculiar to me because as I dug into this more and more, I realized that, well, the amount of data that is available these days is growing explosively. The forecasting models that we use still haven't changed for much of the last 3 decades. And I want to really dive into what I just said. Just in Southern California, advances in data catalog processing and template matching techniques are revealing that even in places that are really well studied already, we're able to reveal, a factor of 10 more earthquakes using these catalog automation techniques that were already available. in conjunction with these increasingly richer observations of seismicity, we have these really cool data sets of the geophysical backdrop of these earthquake sequences, including thermal models, geodetic models, the geology and the rheology of these places, and those don't make it in an earthquake forecast. So that's the question I'll look at the second part of this talk. Can advances in earthquake data translate into advances in earthquake forecast? So attempts to do this really hit a stumbling block, and that stumbling block has a name. It's the epidemic type aftershock sequence model. This is a model that was first proposed by Ogata in 1988, and he proposed to combine some of the canonical statistical laws of seismology into one description of how earthquake sequences evolve as a whole catalog. So in this way, every single earthquake contributes to the probability of having more earthquakes. So every earthquake is contributing to the earthquake hazard. So in this way, we're combining the productivity relationship, which we discussed at length at the beginning of this talk, with the Omori decay, so this rapid decrease in the rate of seismicity after big earthquakes, into an earthquake rate. And what Ogata in 1988 proposed was to use a maximum likelihood method, so to translate this hazard function into an event likelihood. And in this way, you're able to optimize each of the 5 parameters of the class model. But it's not entirely clear how we can incorporate all of these new information into all of these new data sets into a model such as ETAS. For starters, just from the configuration of this model, it's really cumbersome to include very large data sets. In addition, it's not entirely clear how to incorporate something like a geodetic measurement or something about the context, sort of a qualitative information about the context into a model such as ETAS. And finally, since ETAS is so strongly parametrized, even if you knew that something was really important, but you didn't know the exact parametric form, it'd be very hard to sort of understand how an observation would influence all of the other parameters of the ETAS model. So you need to know the answer before you create the model. So without further ado, I'd like to introduce the recurrent earthquake forecast. This is a deep neural network architecture that builds on recent development in data science. In particular, there's been just a series of very high impact contributions in machine learning that are starting to build what are known as neural temporal point process models. These models are aimed at being general purpose descriptions of so-called point process. So any sort of event-based process where you, for example, Twitter posts or sales, all of those things can be modeled as temporal point processes. And you can imagine that there's a lot of incentive to improve these types of models. But in many ways, earthquakes are kind of the canonical temporal point process. And so I collaborated with a team at Technical University of Munich to build a general purpose model for earthquake forecasting. So this is an encoder-decoder model where the objective is to summarize the history of events into a hidden representation for a fixed length vector, which in turn is used to parameterize a mixture distribution for the next event. So in this way, we're doing something very similar to ETAS, right? We took the entire history, we encoded it into some summarized form and decoded it into a PDF of the next event. I want to dive into this really in detail, so to make sure that everyone sort of has at least some intuition for how this model works. We begin with an initialized hidden state, which in turn is used to derive a set of parameters for a Weibull mixture distribution. So each of the components here, for example, here, there are only 3, but there could be any number of components, are used to have a probabilistic representation for when the next event is going to happen. This in turn is used, this function is evaluated at the event time of the next event, and this provides a likelihood for the next event. This next event also is used to update the hidden state using a set of RNN equations. In this case, it's a gated recurrent gate. But all that to say that we took this summarization of the history and updated it with what we just observed. We proceed sequentially through the sequence. And in this way, we have an observation of the likelihood of the sequence given our deep recurrent model. And this provides the same framework to optimize the model, much like ODAP and Vim. So this model has, at the very least, very practical advantages over an ETAS model. As I alluded to earlier, ETAS is a model that requires a reference to all previous events in the sequence to evaluate the likelihood of an upcoming event. In contrast, as we observed through walking through the guts of the recast model, we're only updating the hidden state to create a new forecast. This means that when we consider the entire catalog, that the computational growth is quadratic recast, linear for recast. So this might be a bit paradoxical, but recast with often many, many parameters is nonetheless a lot faster than ETAS. And this might not seem like a huge deal, but ETAS models with fewer than, let's say, 1,000 events to train the model are typically considered to be too unstable to yield good results. However, if you just increase by the observations by an order of magnitude, this is computationally cumbersome and probably prohibitive for most scientists to actually do anything with it. Now, our group did put quite a bit of work into optimizing the ETAS model itself by implementing it in PyTorch and also running it on beefier computers. But nonetheless, it's really hard to run away from this quadratic growth of complexity. In contrast, recast is really well suited to throw these really large earthquake catalogs into the model and see what happens. So like, I think there's a really just practical advantage in using a model such as recast. That's all well and good, but it's not entirely clear that earthquakes are particularly well-suited tasks for machine learning. Catalogs are extremely stochastic. There are few large events that are probably going to have an outsized influence on how earthquake sequences evolve. We also expect that they're going to be very clustered in time. There's going to be very long-range dependency. These are a lot of the elements that typically in a machine learning task you'd be very nervous about. So I think for the remainder of this talk, my goal is going to be to convince you that this is indeed a model that's well suited for this task. I don't want you to take my word here. So the first thing that we do is to develop and train the model in a sort of playground. Here we are generating synthetic data. So we're generating catalogs that are derived from the ETAS model itself to test and compare the performance of the recast model in a sort of playground where we know the answer. So just walk you through the process here. We generate 1,000 synthetic catalogs. Each of those contains roughly 1,000 events or so. We then train both an ETAS and recast model on this set of data sets, and then we can compare the performance of these two models. Let's dive right in. So here, comparing the ETAS and recast model, we can observe the cumulative hazard function of both ETAS and recast on one of these example synthetic catalogs from the test. It's often more familiar to look at, it's more common to compare models in terms of the conditional intensity function. And I hope you'll agree with me that both of these models, at least perceptually, seem to agree remarkably well. It seems that recast is able to capture some of the really sort of peculiar and very specific aspects of ETAS, very punctuated and fluctuates by orders of magnitude. If you want to be a bit more quantitative about this, we can compare the goodness of fit of recast and ETAS, and remembering that ETAS is the generative model here, so sort of in a statistical sense, is the upper bound of potential performance. But nonetheless, a good model should have a lot of the log likelihoods really approach the theoretical maximum performance. So you can see this very skewed distribution, which would suggest that recast is able to capture the ETAS model itself. So to summarize this first exercise, it seems that recast, designed as a general purpose model, is able to reproduce something that's very specific. And this is without any sort of ad hoc adjustments to make that possible. Now that's all well and good, but it is my opinion that real earthquake catalogs are not just an ETAS sequence in real life, but in fact, there might be more in these earthquake sequences than first meets the eye. And jumping right to the chase, it seems that recast for every single model, every single earthquake catalog that we threw at it, recast was the better performing model. And I want to dissect that result a bit more. So here, one of the exercises that we did was to incrementally increase the amount of data available to both ETAS and recast. So here, each of these horizontal white lines is showing this window of observation used to train the model, to validate the model, and then subsequently to test the model on this period. So every single every single log likelihood or every single goodness of fit that I'm showing here is the performance evaluated on the test. And what we find is that for smaller earthquake catalogs, say 1,000 up to sort of 10,000, ETAS is the better performing model. But as we move into these larger earthquake catalogs, these are better fit by the recast model. And I think that this result gives me a lot of confidence into what, or at least I find it reassuring. It makes sense that we've had a lot of really smart people trying to forecast earthquakes, and they've done a really good job on these smaller data sets. However, as these new data sets are coming online in the last 5 years or so, these have not been explored in as much depth. And in fact, I think this is where machine learning can really shine. And this is, go ahead.
Is there physical meaning behind why ETAS works better for small catalogs and recast for bigger ones? Is there something about the process that you've learned? Maybe this is a question for later. But there must be a reason why people should use this.
Yeah. So
You'd think you could always do better, right?
Yeah.
I think it's a quite consistent pattern where, like, if you observed a process for a very short amount of time, I think a very crude model would work very well. But as you observe things for longer, you start being able to confidently say that, like, on data from the future, there might be actually second order effect, and so on and so forth. And I think so. ETAS is a very crude model. It's like it's this example. For example, if I was looking at, I don't know, weather, initially I might just have a very crude model of like the average weather that I've seen over the last sort of fixed amount of period might be a pretty good prediction. But as you see, weather for multiple years, you might start saying, oh, there are patterns, there are seasonal patterns, and so on.
Are you normalizing somehow that for the magnitude? Because as you have these larger catalogs, you have much more smaller scope.
Mm-hmm.
And so you may be predicting your likelihood will be stronger because you're better predicting a small one.
So this is something that I was quite concerned about, and I would love to do this comparison by just diving deeper and deeper down into the catalog completeness, but to avoid that specific effect, we instead considered longer and longer periods with consistent magnitude cutoff. So that was at least my attempt to avoid that specific effect. And this kind of takes me to my other point, that I was quite concerned that it also might be some artifact of this particular catalog. Maybe its processing was weird in some particular way that was well suited for recast, but not necessarily well suited for ETAS. But in fact, all the catalogs that we tested, and that includes this subregion generated by White and his co-authors, the entire Southern California data set, center catalog, as well as the QTM catalogs, and then sub-regions of the QTM catalogs. All of those indicated that, at least in terms of goodness of fit, it seemed like this recast model was outperforming the Cyclone recast.
So can I ask one question? The SC, EDC entire region, you are using one ETAS model, like a 5 parameter? It doesn't matter. It should be different, right? Even though people ETAS space and time.
Yeah, so, well, I think that's a very valid objection. However, I think part of the reason we also tested these smaller regions was to see whether this was actually a concern.
Right.
And when we tested on the smaller regions, we actually get even more improvements. So at least our sense was that that was not a primary effect. And it's also worth noting that like recast is given the same information as the ECAS model. So
I see. I see.
that. So this performance on a lot of different catalogs at a lot of different scales would suggest, at least to me, that it's not an issue about completeness or processing techniques or sort of spatial component that is really driving this improvement. I think it's really that recast is a more flexible model and is able to sort of adapt to how these different sequences are evolving. Now, I don't know about you, I don't even have a great intuition for what it means to have a unit increase in log likelihood in terms of goodness of fit. And in fact, the more common use case for these models is to examine sort of forecast over some fixed amount of time. So this is the standard forecasting task. We have a smaller quick sequence and we would like to know what's going to happen in the next 2 weeks. So for the remainder of this talk, I'll be using the Southern California Data Center catalog, and again, I'll emphasize that we also tested on the other smaller regions and we have similar,
Thank you.
we have similar results. So recast is actually quite well suited for this, and in particular because of the choice of a Weibull mixture distribution, we can just seamlessly just sample from the distribution itself. And this affords a lot of computational efficiency, but also just makes it really easy to generate a lot of earthquake sequences or catalog continuations. So here's an example of what this might look like. So now we've filled in this 14-day interval with the cumulative number of events that was actually observed in black. Then each of these gray lines is one simulation of what could happen in the next 14 days. And for someone like me that spends a lot of time looking at earthquake catalogs, I think this is already really cool in that we see that some of the simulations have these large bursts in seismicity, for example, simulating cascades of aftershocks, but that the vast majority of outcomes are actually quite close to the observed outcome. So the observed outcome is really close to the modal outcome if we do a lot of these simulations. So here we do 50,000 catalog continuations, and we now have this objective way to say, like, is this a good forecast or a bad forecast by essentially just saying how many times was it exactly correct. So the rate of exactly correct forecast will be how we say this was a good forecast. So this figure has a lot going on. We saw the top 2 panels already. But we compared this rate of accurate forecast over the entire test period of the Southern California Earthquake Data Center catalog. And this orange curve is tracking the relative performance of the recast model and the ETAS model throughout this period. When the orange curve is above the dashed line, it would suggest better performance from the recast model, and below would suggest that our benchmark model is pretty performant. So for the vast majority of this test period, recast is significantly outperforming the ETAS model. And I think something quite remarkable to me was that even during the Ridgecrest sequence, which is included in this test period, the ETAS model has no accurate earthquake forecasts. In contrast, recast is still able to have some accurate forecasts. So that's why these markers are like all the way up top. And then as a final note, none of the models are predicting Ridgecrest or predicting there's going to be a sudden burst in seismicity. So this is what this marker right before the Ridgecrest is. Yes.
So it seems to trump down suddenly whenever there's sort of bigger aftershock sequences. And that maybe makes sense, right? Because that's more ATAS like the regular major aftershock. Is that what's happening?
So particularly in the Southern California data center catalog, the training period by no like sort of choice of our own is the 80s. It's Hector Mine. It's a lot of big sequences. It's a lot of seismicity. This period, the test period, typically lower seismicity. So ETAS is like very consistently kind of overpredicted. So you can imagine that if you took like the most crude example of this might be that if you just took the average of your training set and use that as your prediction for the test set, you would do well when the seismicity is high because your test set was high, and you would do worse when your seismicity is low. But I'll note that that's a characteristic of this test. We've done other tests where it's more that recast is able to track how the seismicity evolves, rather, whereas ETAS is less sensitive to the fluctuations.
Can you give us a sense? So you said, I mean, you show here that recast is doing much better than ETAS. I see the orange line is above the red dashed line, but can you explain to us what this really means? So in an aftershock sequence, you just had that magnitude 7.1. What is the difference between what ETAS is telling you is going to happen and what recast is telling you is going to happen?
So we talked to the folks at USGS, and we were like, what do you care about? Like, what is important when you generate these forecasts? And I don't think that they have ambitions of predicting an earthquake, but something that's quite important to them is to avoid surprises. That's what they call it, the rate of surprises. So they publish 95% confidence intervals. And when they're retrospectively testing their forecast, they ask, like, how often will we outside of the 95% confidence intervals? And they're still finding that quite often they're outside of those intervals. And that requires them during sequences to make on-the-fly decisions to adapt their models if the sequence seemed to have different parameters and so on. We did this comparison. I'm not sure I have it easily accessible. Maybe I can show that. And the rate of surprises is like 3 times smaller for the recast model. And I think that that's quite important because I think as a governmental agency, for example, you don't want to lose face. And so that's an example of like a pretty practical difference in terms of if you're like an operational agency. So this is an example of what the confidence intervals look like. So that those are the 95% confidence intervals and the median prediction. So this brings me to my final conclusion of this talk, which is that it seems like on synthetic catalogs, our general purpose model that wasn't sort of custom tuned to earthquake sequences was able to capture what we know are in earthquake catalogs. That's sort of the state of the knowledge. But however, on real earthquake catalogs, it seems like there's improved performance in terms of model likelihood, and also that just the vast majority of forecasting intervals are better forecasted by recast. And I hope at this stage I've convinced you that like I've done my due diligence and like it's at least doing it as well as ETAS, and that this is a well-suited problem for machine learning. That's if you leave and I've convinced you of that, I'm very happy. But I think it really scratches the surface of what we can do with machine learning and earthquake forecasting. So I think they're very interesting sort of scientific questions that we can ask by seeing now as we introduce different geophysical observations into a forecast, does it improve the performance? So like the model might be a bit of a black box, but we can still use a black box to do science. And I think that's a very important thing to appreciate. In addition, we can also forecast other aspects of upcoming events. So I've shown an analysis where I'm generating a probabilistic description of when the next event is going to happen. But we can do that for the magnitude, we can do that for the location, and I think that has just very practical applications. I think there's a lot of room to improve spatial forecasts in this way, for example. So to wrap everything up, I'd like to suggest that forecasting by analogy to previous events that we know are sort of geologically similar, I think is a very interesting and complementary approach that could that also helps illuminate sort of the physics of what's going on. So I think, and then as I moved on to what I think is a really promising approach in the future moving forward, the neural point process models such as recast have the potential to translate the abundance of data into better earthquake forecasts. And I think that's something to aspire to. Thank you.
We have 5 minutes for questions.
How does the false positives compare with ETAS and recast?
What would be a false positive?
And like your prediction is false, it should happen.
Also,
very important for any machine learning model, right?
Well, so here where it's a bit different, we're training on the likelihood of the observation. So there are ways to sort of turn this into a model that is trained on the true positive rate or the false positive rate and so on and so forth. But this is a bit different in terms of like the cost function that we're using to optimize the model. If you would like to examine the false positive rate of, say, a really big earthquake happening or not, you could do that with, for example, a trained model where you would generate a bunch of sequences and then examine the statistics of those catalog continuations and say, like, was there one magnitude 5 or was there a magnitude 7? So that's a way in which that can be used. And then the final note is, whereas it's typically kind of hard to, ETAS is very well suited to be trained on the maximum likelihood itself. Machine learning is very well suited to swap out your cost function. So it's very modular in that way. So if you are sort of an end user that cares about, my building here and how it's going to be influenced by seismicity, you could actually incorporate different cost functions. And I think that's like a potential area of growth where you can very easily swap in and out different aspects of the model that are more important to you.
Harriet?
No, I was wondering if recast had potential for a data assimilation, or if you had to actually retrain your model each time your catalog was growing, or do you have a way to just branch in the new observations as time goes by?
I don't know. Not gonna speculate. I don't know. I know there's like a big area of data science that's focused on these models that can do data assimilations. Yeah.
Harriet?
Yeah, thanks, Kelian. It's just interesting because I think quite a lot of us know that Wei Chen is going to come, and it'd be a really cool person to connect with. You probably know him, I don't know. But I was going to ask on the first part of the talk, and I don't really know how to pose a question, but you kind of touched on it. But you had all these parameters that could try reduce the variance, right? And then you sort of said it at the end that actually really what somewhat matters is the fault availability. And so all those parameters somewhat covariant in that regard. So I was just wondering, is a parameter like fault availability of better problem, could you get better variance reduction if you somehow combined all this? And so you were kind of considering them individually, right? And of course, if there is some covariance, then maybe you could get a better variance reduction if there was.
I mean, that was the aspirational thought behind using sort of support vector.
Right, right.
And kind of bootstrap the different parameters and see at least like which ones are kind of redundant and which ones provide more complementary information. That was the intent behind that, and it seemed that like the plate age, some measure of like how compact the rupture is and the dip of the rupture were really the key parameters. And you can kind of imagine how those are actually pretty orthogonal.
Right. Yeah, I was going to say, yeah, cool.
So maybe also related to that question and the first part, when we think about aftershock, we think of it as sort of being a combination of some unknown contribution of static stress triggering, dynamic stress triggering, and triggering by post-seismic after slip, maybe other relaxation processes. So if you have that in mind, does that help with separating things out? Because it's again sort of a combination of source and environment.
I mean, Emily might not like that I say this, but I think like we tested radiated energy, right? And that one really doesn't seem to have a ton of influence. One of the things with a lot of these effects is that they kind of have like opposite effects. So for example, ruptures with high stress drop tend to have more radiated energy, but that stress drop translates into more slip in a smaller area given that magnitude. So you have these effects that are kind of countervailing.
Right. So then maybe what matters most in the end is again that volume of availability.
I think that's like
yeah.
I think a good conceptual model. And as I kept track of seismicity, I think a lot of subsequent observations really match with that. Yeah. I encourage you to think about that in the next earthquake of the week, like offshore oceanic events tend to be really deficient in aftershocks. Convergent boundaries tend to have a lot of aftershocks.
And Brent, do you want to unmute yourself and ask your question?
Can you hear me?
Yep.
Oh, great. I was curious if we've been using ETAS to infer the physical parameters from these catalogs. Doing this analysis, do you think we're getting some biased estimates in those physical parameters?
Well, that's very interesting. So it's very well known that the parameters, like one of the really tricky issues in ETAS is that the parameters covary quite extremely. So, so you end up having to play these games where you hold one parameter and you interpret all of the fluctuation to live in another parameter. So like to some extent, I am kind of a bit nervous to like dump everything into one parameter, but yeah, I think that's a large topic that a lot of people have thought about, and
I guess another way of asking my question is your very first plot that you showed.
Yeah.
Showed a large spread in the range of aftershock production rates.
Mm-hmm.
If we re-estimated those using recast, do we get a more sharply peaked process? Or is it still really broad?
I don't know how to answer that question. I'm not like, I think recast is not. I have to think about it more. I'm really not sure.
All right, cool. I was just curious.
Brent, come to the balcony on the second floor.
Okay, all right. I'll be right there. Just give me like 6 or 7 hours.
Yes, so you showed that your recast model does a better job than the ETAS. Yeah. So I think, as we know, the ETAS is based on it's like a combination of our known knowledge, like physical constraint on the earthquakes. So if your model has a better job than the ETAS, does it mean like there is some physical, like physics of the earthquake we didn't consider before?
I think the main physics, and it's not particularly like exciting, but I think a real thing that is happening is that, quote unquote, your ETAS parameters are changing during the sequences. And how to do that in an ETAS model, it's doable. Like there are non-stationary ETAS models that like let the parameters change over time. But a lot of the benefits of ETAS, like being able to look at the parameters, you lose them in the process of making your non-stationary models. And I think this is where machine learning is able to kind of contribute a very like formulaic and straight and very rigorous way of how to deal with these problems of changes within your training set, changes beyond your training set. So I think that's at least the key scientific insight that I read from this benchmark study is that the Earth changes in time quite a bit, and having a model that is autoregressive and is able to keep track of those changes is quite important.
Any last questions? No, then we'll head to the balcony and thank Kelian again.